Okay, so welcome back to the course on our course on fundamentals of attosecond science and technology, FAST, which we bring to you from IIT Madras and IIT Tirupati. So we are now in a position to enter into the third module of this course, which is on nonlinear optics, but right away I must say it's in a nutshell. So we will delve into that. Once again, the references, I still stick to our key texts, which remain the same as before, but I will be putting forth some lecture materials from other, say, relevant textbooks as we speak, but I am not enlisting them because it would probably be a little too much on the student to have to refer to more than 4 books or so, but I have cited them in the slides, so you can pick up on further details. There are at least a few very good and authoritative texts on nonlinear optics, where you may like to look into, especially if you have interests beyond what this course is going to bring up for discussion. And of course, thanks to Professor Trevino for his slides. But the outline of today's lecture itself, I will still have to do one little section from the previous lecture, that is on time bandwidth product. So, I will complete that and then move on to the nonlinear optics primer, or in a nutshell as I have called it. Okay, now for the recap. Okay, I think you are going to scream at me saying stop showing this slide, but it is really important in my opinion that that should now be the idea of optical light pulse in our minds, which, as you can possibly now read off, it is like a linearly chirp pulse, positively chirp pulse, and that propagates and the direction of time is from left to right, increasing direction of time. And we now are experts, I suppose, in writing down the complete electric field description of this ultra short laser pulse in the time domain, as well as its Fourier transform in the in the spectral domain, so that you, from intensity and phase in the temporal domain, in the frequency domain, we go to the spectrum and spectral phase. Okay, so now both the phase functions in time and in the spectral domain are not what we know a priori, very likely that is the scenario. Instead, we have to think about these in the sense of a Taylor expansion. So, we have the 0th order phase, which we call the absolute phase, the initial phase, or this even the carrier envelope phase for very short pulses, and we have the higher order terms, where the first derivative at t is equal to 0 is related to the instantaneous frequency, and then in the frequency domain, which is our go to domain, because that is where more often than not, or almost always, measurements happen. So, that there the coefficients phi 1 and phi 2, we interpreted them as group delay and group delay dispersion. So, we had this sort of iconic thing about the yin and yang of describing pulses, intensity and phase, and we even addressed the question of which aspect is more important, right. So, we took two pictures here, the pictures of Professor Trevino and Linda. This is the example he has so nicely illustrated. So, let us say the male and the gentleman and the lady in these pictures. So, now these are the original pictures, and what do? We essentially take the intensity profile from the lady's picture and use the phase profile from the gentleman's picture and construct a sort of hybrid by inverse Fourier transforming, where the phase profile, the spectral phase is kept intact, whereas the intensity is mismatched. Okay. This is taken as the input for the inverse Fourier transform. Likewise, in the corresponding case, for reconstructing the lady's picture, you use the gentleman's spectral intensity, but retain the spectral phase of the lady and take that as the input for the inverse Fourier transform. What do you see? You see that in both cases a significant part of the significant features that are in the picture are retained. So, indeed phase plays a very critical role. The spectral intensity itself is something which is not unimportant. It does add to the the clarity of the picture and so on, but we can still recover a significant amount of features by employing the correct phase map. So, as I said, in certain problems, in scenarios where we have inverse problems, where we have to more or less guess the phase profile, it can happen because we do not directly measure phase, we are given intensity profiles, right. So, then in scenarios where we have to solve inverse problems, it becomes a problem of finding the right phase profile. Okay. Then we address the next thing in relatively great detail in the previous class, where we considered the question about what happens to a pulse propagating through a medium, right. So, in this case, the medium itself has linear response. That is really important to note, because in today's lecture we will start going into nonlinear response of media. Okay. So, we always model the propagation of a pulse in the frequency domain rather than in the time domain for a variety of reasons. Okay. So, variety of reasons in the sense, measurements themselves are made in the spectral domain or the frequency domain, and things become quite well, also numerically easier or efficient in the frequency domain. But the more important point is the following: in order to describe the properties of the medium, we of course need the refractive index n, which depends upon frequency, but then we also need to know the absorbance of the medium in the frequency domain, where absorbance comes from the Beer-Lambert law, as we saw in the previous lecture. And note here that it is alpha divided by 2, because absorbance is arises out of the logarithm of the ratios of essentially the input intensity versus output arising out of Beer's law. Maybe I can even like very quickly just write the two notions down. The intensity after propagating a length L is the initial input intensity multiplied by alpha times L, and therefore, if we now consider the logarithm of the input versus the output intensities 1 by L. So, this is absorbance. Okay. And so, therefore, alpha corresponds to the intensity domain quantity, and and note that I is proportional to the absolute value square of E, or E scales as the square root of I, something we have already seen. Therefore, a factor of half manifests in this equation, and this is to say that alpha should be considered as a quantity measured in terms of intensity ratios. So, when we propagate a pulse, we write this expression out, separating the real and imaginary parts of the of what could be a complex refractive index, which I introduced to you in the previous lecture. So, n tilde is n omega plus I times a kappa of omega. Kappa is related to the absorbance of the medium, both of which are frequency dependent. And we have here, after writing this expression out so that we separate the phase versus the amplitude terms. So, this is the phase term, and this is the intensity term. Okay. If we write these two pieces out, then we essentially have, as a consequence of everything else, the spectral phase part is basically the argument to this exponential function. But note that E in, okay, E in also has an amplitude and phase dependence. E in of tilde is also a complex function. E in of tilde is square root of S in of omega exponent of I phi in of omega, all right. So, this goes through the medium of interest and comes out as E out of omega, where we would of course have S out phi out of omega, where S out and phi out are enlisted here as they are. So, it is S in multiplied by exponent of minus alpha L, whereas here, so therefore, the attenuation, okay, the attenuation of the wave due to finite absorption is multiplicative in its effect. It's multiplied to the spectrum, the spectral intensity as a function of frequency, whereas the additional phase, the delta phi that the wave gathers due to propagation becomes an additive effect in terms of the modification of the input phase function. So, input phase plus this quantity which I could, the quantity which is n of omega by C L becomes an additive change delta phi. So, this is the delta, maybe I just write it down as, so this is phi in of omega plus delta phi of omega. Okay. Now, this is a bit new. Okay. We are for the first time in this course, we are making a foray into some aspects of pulse metrology measurement. I am still not going to discuss anything about how, but at least some measure of things comes into our discussion for the first time. So, this is again the classic problem. We have the shortest events produced by mankind and known to mankind, and how do we measure its duration, right? How do we measure the duration of the shortest events? So, this is the classic problem where you have a clock and then we start questioning its, if we doubt whether the clock is keeping the second properly, any clock for that matter, be it in a digital or analog, we start questioning its integrity or fidelity, whatever we call it, maybe we should call it fidelity of the device, right. There, because there is no way to verify, we need to compare this with another standard clock, but that is the problem here. If we have the shortest events available either to the whole of mankind or within the reach of any researcher, you, me or anybody, then what is the, how do we get even define a measure for these things. So, the first and the in a way the simplest measure for the width of the pulse is the following. So, there are many definitions, we will come to more sophisticated definitions, but then a simple idea to get a measure of the width of the pulse is the following. The effective width is the width of a rectangle whose height and area are the same as that of the original pulse. So, you preserve the height of the pulse, okay. But then we take the area under this curve. So, the area under this curve is some bit of energy, okay. A single pulse can have an energy of some nanojoules or microjoules or millijoules, or if you dare to even joules or tens of joules, hundreds of joules. A kilojoule is huge, especially if you consider pulses whose durations are of a femtosecond order, then you can quickly do the math even in your heads and minds. If you take a pulse of hypothetically a femtosecond in duration, which is very short, if the pulse has a femtosecond in width, then you have the energy of the pulse, you can compute the power, or what we would call the peak power of this pulse, which is essentially the energy divided by the duration, right. Energy per time is power. So, if I take femtosecond 10 to the minus 15 and take a nanojoule pulse, a pulse containing just 1 nanojoule of energy, really a small amount of energy, then the power that I can associate with this pulse would be 10 to the 6 watts. Right, 10 to the minus 15 seconds and 1 nanojoule, 10 to the minus 9 joules, whereas here it is already a gigawatt. So, a megawatt, a gigawatt are the kind of powers we usually talk in terms of power stations. 100 megawatt is not a huge power station, but that is at a gigawatt starts to become the kind of power a city wants to consume almost of gigawatts of energy, right, of power rather. Whereas this is after giga, what is the next? 10 to the 12. Okay. 10 to the 12 is a petawatt. That is incredible. And 10 to the 15 is how much? Oh no, sorry, this is terawatt, not petawatt. 10 to the 12 is a terawatt, 10 to the 15 is a petawatt. These are huge amounts of power, right. So, no power station in this world, I think, produces a petawatt of continuous power. But then we start to compare this with maybe astrophysical dimensions. What is the amount of power, radiative power falling on the surface of the earth from the sun? We could ask questions of that nature. Take all that energy and how much energy is incident on the surface of the earth from the sun. We've got to start talking about it. Then we can say, okay, what about considering the entire amount of power radiated by the sun out, or a typical star of that size. So, then it starts to get petawatt C and maybe even higher. So, we are now going into the realm of astrophysical objects. Anyway, just to give you just a feel for the kind of numbers that we are dealing with in this case. Yeah. So, basically the effective width of a pulse is not a bad measure. It's a good measure which is easy to understand, but the point that we need to appreciate is that when I integrate the area under this curve, I am determining the pulse energy content of the pulse or the pulse energy. I am preserving this pulse energy. Energy has to be conserved no matter what. So, I conserve the energy, but in order to get a robust measure of the width, we also keep the height constant, saying let the maxima of the two match, and let us only try to figure out what the effective width would be when we conserve the amount of energy in the pulse, right. By the way, no laser on this planet can give us a continuous beam of megawatt. Megawatts, yes, there are continuous lasers, gigawatts and so on. It's really hard. Okay, maybe in the case of radio waves, I don't know, but I think there also it would be pulsed. But the point being, all the power that you need to radiate out of a laser would have to come from a wall plug. So you need to do something about that. Okay. They are nanojoules. Okay, the question was what is the current energy per pulse in the case of attosecond pulses. It's typically tens of nanojoules. Now there is work going on to make microjoule pulses, but I must quickly add that this is when I say tens of nanojoules, when I say tens include hundreds also in cases where one can be a little more ambitious, maybe with bigger laser pulses and from attosecond pulses produced by relativistic plasma sources, they can be pretty energetic. So, single pulse energies there could possibly be higher, whereas as of today, to the best of my knowledge, for microjoule pulses at similar wavelengths, one has to go to a free electron laser, which is an accelerator based photon source. But for whatever it may be, the effective width is area divided by the height, very simple measure. Okay.